Okay, in section 4.1 we talk about the local max and the local min. Now in this section we are going to talk about the global max and min. So let's see the differences between them. If you take a look at the graph here, if we consider around this area, then we can say that this point is the lowest value, or we have the local mean from section 4.1. However, if we compare this point to the whole interval from A to B, then it is not the minimum value, because this point is lower. The value is even lower than this point. So the point that is the mean value of the whole interval from A to B, we say that this point is the global mean. The same thing to the local max. If we only consider around this area, then this point is the max value. However, if we compare to the whole interval from A to B, then this point is not the max, but instead this point is the max value. So we say that this point is the global max. However, the global max is also the local max of around this area. If we only consider around this area, then this point is also the maximum value, or we do have the local max. The same thing here. The local mean is also the global mean, because if we only consider around this area, then we do have the local mean. Now, for this graph on the left here, we do have the endpoint of A and B. However, on the left, on the picture on the right here, we do not have the endpoint. We do not include the endpoint. Therefore, we cannot find the largest value of the graph because we don't have the endpoint. Now, if we don't have the max value of the whole graph, then we can say that we have no global max, because we do not have the endpoints, and we do not have the largest value. However, we do have the local mean and the global mean for this graph. If we take a look at this graph, this point is the global mean because it is the minimum value of the whole graph here. And if we only consider around this area, then we also have the global mean at this point too. Now, we also have another local mean around this area. If we only consider around this area, then this point is also the mean value. And we do have the local max, even though we don't have the global max. So if we consider around this area, we do have the local max. But this point is not the maximum value of the whole function, and we cannot say that this is the global max. And again, we cannot have the endpoints for this graph, and we do not have the largest value. Therefore, we don't have the global max for this case. Now, how do we find the global max and min? So, in order to find the global max and min of a continuous function on an interval including the endpoints, so make sure that if you find a max and a min, pay attention to the endpoint, because this is really important. Now, first compare the values of the function as all the critical points in the interval and at the endpoints. So if they give you a function, the first thing is we have to find the critical points, and then using the value as the critical points, plug in that value to your original function, and also plug in the endpoint to your original function, and compare the value, which one is the min and which one is the max. Now, in the case that we exclude the endpoint, first find the value of the function as all the critical point, and then sketch a graph, and you see which one is the max and which one is the min. We'll see this shortly. So let's go over one example. Hopefully it will make more sense. So the first example. So find the global max and min. So find global max min of this function. So f of x equal x to the third power minus 9x squared minus 48x plus 52 on the interval minus 5 to 14. So again, the first thing is they give you the interval and the function. So the first thing we should do is we must find the critical points. And in order to find the critical point, we need to find the f prime and then set that equal to 0. So find f prime. Now, using the power rule is easy. Bring down number 3, subtract 1 from that, bring down 2, minus 2 times 9, 18. Subtract 1 from that, and then bring down the 1, which gives you only 48. The constant becomes 0. Now, after you find f prime, right, we can factor out the common factor number 3. So if you do that, you get x squared minus 6x and then minus 16, right? And this expression can be also factored into x plus 2, x minus 8. So x squared minus 6, x minus 16 can be factored into x plus 2 and x minus 8. Now, once you find the f prime, set that equal to 0. So I set this whole thing equal to 0 to find a critical point. Now, once I set that equal to 0, I get what? I get x equal minus 2 and x equal 8. Okay, so these 2 points are the critical point. Okay, now we need to test the value in order to see which one is the max and which one is the min. Don't forget the endpoint. We use the original function. We test f of the 2 endpoints. So f of minus 5 and then f of 14. We also test the critical point. So f of minus 2 from here and f of 8. So if you plug in minus 5 for your original function, you're gonna get minus 58. If you plug in minus 2 to this function, you will get 104. If you plug in 8 to this f of x, you got minus 396. You plug in 14 to here, you get 360. Okay. So once we have all the value, we can see which one is the global max, which one is the global min. The global max, of course, is the highest value, and global min, of course, is the lowest value. So out of the 4 value here, 360 is the highest, or we have the global max here, and this one is global min. Okay, so that's how you find the global max and global min from the function. So first, find the first derivative, set that equal to 0, find the critical points, and then plug in that critical points and also the endpoint to your original function and compare the value. Okay, let's try another function. So here we have the problem. So for the time t bigger than 0, and this is in days, the problem say that the rate at which photosynthesis take place in the left, okay, of a plane represented by the rate at which oxygen is produced, and is approximately by P of t equal 100 exponential minus 0.02 t minus e to minus 0.1 t. Okay, the question asks us, when is photosynthesis occurring fastest? And what's the rate? Okay, so the problem gives you the photosynthesis equation of oxygen. Now it's asking you when. So when is the time? So it's asking you for the t. So when is photosynthesis occurring fastest? Or when is the time that this function gives you the largest value? In other words, we are trying to find the global max for this problem. And what is the rate, or what is that value? Okay, so again, in order to find the global max, we must find the critical point. All right, so in order to find the critical point, first find the first derivative, or p prime of t. So I'm gonna find p prime of t. Now this problem, you can first let's just rewrite the problem. P of t is 100. Just multiply 100 to the inside. So minus 100, 0.1 t. Now if you take the prime of t, 100 stay the same. So exponential function, we stay the same. We bring down the constant, so multiply by minus 0.02 down, and then again minus 100. Again, exponential function stay the same, but we bring down any constant we have down. Okay, so we have this function here, and let's simplify this. 100 multiplied by 0.02 is going to give you naturally we don't have to. Now let's just set it equal to 0. That means we can bring this one to the right hand side. So I have 100 e to the minus 0.02 t and multiply by minus 0.02. So we bring this whole thing to the right side because this is a 0. 0.1 t and minus 0.1. Right. The reason I didn't want to multiply 100 to here, because now we can cancel. We can divide both sides by 100, right? And let's move the exponential to one side and the number to the other side. So if I divide both sides by e to the minus 0.1 t, I have this e to the minus 0.1 t per 1. And then also I divide by minus 0.02 to the right. Okay, and if minus and minus become plus, right? And 0.1 divided by 0.02, that's going to give you 5. And also, if we divide by the two exponential function, we have the same base, so we just subtract the exponential together. So we have exponential minus 0.02t minus 4 minus become plus 0.1t, right? Or if we simplify this together, we can add, because they have the same, combine the like term, we get e to the 0.08t. And we add these two together. Okay. Now eventually we have what? We have e to the 0.08t equal 5. Okay, so let's try. Let's solve this for t. Okay, so we have 0.08 e to 0.08t equal 5. Now we need to solve for t, right? To find a critical point. In order to solve for t, take ln on both sides. ln e to the 0.08t, ln of 5, ln of e is cancelled, so we have 0.08t equal ln of 5. So solve for t gives you ln of 5 divided by 0.08. That will give you about 20.12 days. Now, because this function did not have the endpoints, another way to test to see if this value is the local max or the global max, we can use the second derivative test. Now, because we only have one critical point, so this point may be just the local max, right? So in order to find if this is really the maximum value, we need to find b double prime of t. So again, remember, our p prime of t is what? Is 100 multiplied by minus 0.02 e to the minus 0.02 t plus 100 0.1 e to the minus 0.1 t. So if you take another p double prime from this one, you're gonna get what? Again, we keep the constant together. So 100 0.02, exponential stay the same, and then bring down the constant down one more time. Okay, and then the same thing to this one. Exponential stay the same, and then bring down the constant. Okay. Now, if you simplify this, you're gonna get minus and minus multiplying together give you plus. So 100 and 0.0004 e to the minus 0.02t, and this one minus and plus give you minus 100. 0.1 times 0.1 gives you 0.01, and e to the minus 0.1 t. Now, the reason I'm asking you to find b double prime of t, because if we use this critical point t equal 20.12, if we plug in the value for b double prime, let's try that. So b double prime of 20.12, this is the only critical point we got for the problem. So if you do that, if you plug in 20.12 into this formula b double prime, which is this one. For t, which is 20.12, you're gonna get minus 0.107. This one is what is negative. So remember, if your second derivative is negative, you got what? Negative, you got the sad phase, right? Or if we have a sad phase, that means the function is concave down at this critical point. Concave down is this one. If we have the concave down at this point, that means we have what? We have the local max. Or we can say that this one is also the global max. If we only have one critical point, and this critical point gives the second derivative to be negative, or we have the concave down, which means that this critical point is in fact the global max value of the function. Okay, so now we have the critical point. We can plug in this critical point to. Now they ask us to find. So the question is, when is the photosynthesis occurring fastest? We can say that as 20.12 day. So at this time, the photosynthesis occurring fastest. Now, what is the rate? Remember, they give us the P of t formula, so we just have to plug in this value to find the rate. If we do plug in this value for P of t from the beginning, you got 53.50, or the rate is 53.50 unit of oxygen per day. So this is the two answers we should have for the question. So again, if we only have one critical point, then we can also use the second derivative to test for the value. This is negative, that means we have the concave down, or you can have the local max or the global max for this case. So that should be the end of section 4.3. It's basically using the first derivative to test for the critical point and the end point to find out which one give you the max value of the whole function, or which one give you the mean value of the whole function. Okay, if you watch this video by Thursday, email me. I'll give you 1 point for the extra credit. Thank you.